Okay, so at this point is where we go from electric to magnetic fields, and we'll mostly be talking about magnetic fields from this point onward. And the first thing that I wanted to point out is the great similarity between electric dipoles and magnetic dipoles. A magnet, a typical magnet you might find in a science store or something like this, might look like this. And I think the usual convention is red is North Pole and blue is South Pole for a magnet. We don't have positive and negative magnetic charges. We just have these poles, which are called the North Pole and the South Pole for reasons that you'll see in a minute or two here. Now, you see that for an electric dipole, you have field lines, electric field lines that go from the positive charge to the negative charge, but they stop. Contrast that with the field lines that we've drawn for the magnetic field around a bar magnet. Those go from the North Pole out, they curl around, they go back in the South Pole, but inside the magnet, if you're inside the magnet, they're going from south to north. If you're outside the magnet, they're going from north to south, which leads to endless confusion and frustration. And one reason why is due to the Earth's magnetic field, which we'll talk about in a second. But you can see that if we cover these things up and just look at the electric field lines or the magnetic field lines, it looks pretty similar, right? It's pretty difficult to tell the difference between these two. So I can understand how when you look at these two pictures, you might think they're basically the same thing. But they're really not. They're really not. Magnetic field lines are always loops. They always go all the way around. So if you're ever asked to draw a magnetic field line on a diagram, and I believe you will be, then it should be a continuous loop that goes all the way from south to north inside the magnet and then north to south outside the magnet. And of course, these magnetic field lines are in 3 dimensions, just as they are for electric fields. Now we have a nice demonstration of the magnetic fields surrounding a bar magnet, a dipole magnet. I think I can get this up on the screen here. What we have is just this little plastic thing, and it's got liquid in it. And I don't know if you can see this, but the liquid, I don't know if there's a light on the... Whoop. Now, what I'm going to try to do, is there an external light? Well, we'll see how this works. I'm going to take this magnet with its poles aligned like that and put this on top of it. And the iron filings inside this liquid tend to align in the direction of the magnetic field lines. And if we let this go for a while, shake it up a little bit, you can start to see the pattern forming, which is very much like the pattern that we had with on the screen with the other one. Now, I thought I got better results with this big honking magnet over here. Don't bring your credit cards up here. It will erase them. But that's the field pattern you get from that one. I don't know. We can shake it up like an Etch-a-Sketch and get it sort of erased and then put a magnet underneath it. We can come back and see how its pattern develops after some time. Let's that one go. All right, I'm going to let that go. We'll come back to it in a few minutes. See how it develops. So now, if you have a uniform magnetic field pointing to the right here, a bar magnet will tend to align such that it's pointing in the same direction as the magnetic field. Now remember, the field lines are inside the magnet are going from south to north, and they're concentrated, meaning the magnetic field is strong there. Then outside, the magnetic field is weaker, where the field lines go from north to south. The net effect is to tend to align the magnet with the magnetic field. Now, as you know, the Earth has a magnetic field, and we use a compass, and a compass is just a permanent magnet, where you paint one end red. So if I spin this compass here, it should end up pointing in the direction of the Earth's magnetic field. Now we know that this building is aligned north-south, and that's the north direction. But the north magnetic pole of the Earth is about 13.6 degrees to the right, to the east of it, over in Canada, north of about Chicago. And indeed, when this thing settled down, that's the direction it pointed. Now furthermore, the Earth's magnetic field points down into the Earth, and this compass is actually trying to do that itself. You know, if I set it straight, it likes to point down along the magnetic field lines of the Earth. Now, if there's some other magnetic field around, we can affect the direction of the compass. This is a pretty strong magnet, permanent magnet, and if I move it around, you can see that the compass is pointing in that direction away from, away from the magnet wherever I go. In fact, you can actually turn this into kind of a motor if you're clever. There we go. So just by waving the magnetic field at the right frequency, I can get this thing to turn. That's exactly how an electric motor works. Now, the problem is the Earth's magnetic field is not what you necessarily think it is. Okay? Now here we've drawn a picture of the Earth, and there's a giant magnet which is thousands of miles long. It's trying to say that the Earth acts like a giant magnet whose north pole is down here and whose south pole is up here. Wait a second, that's South America, there's North America. I thought we said the north magnetic pole is up here. Yes, the north magnetic pole of the Earth is actually a south magnetic pole in the sense that the field lines are going into it. And they're coming out of the Earth in the southern hemisphere and going into the Earth in the northern hemisphere. Also, if you look on the edge here, you can see that the field lines have this angle to the Earth's surface that I was talking about. It's about almost a 45-degree angle. Wait, I think I calculated it. 30 degrees here at one point. Anyway, it's pointing down into the Earth here in Northern California by about that angle. So it's a little bit confusing because what we said is a north pole is where the field lines come out and go back in. And we also said that if I have a magnet whose north pole painted red here is like that, it tends to align with the Earth's magnetic field direction. I'll stop it. It wants to point in that direction. And that's because the field lines outside of the Earth's surface are pointing in the opposite direction that you might expect, according to this picture, which I'll get back to. Like so. So yes, the south pole of the Earth is a north magnetic pole, and the north pole of the Earth is a south magnetic pole. If you just remember that, you'll get completely confused. Don't worry. How does the Earth's magnetic field get generated? The Earth is basically a big ball of iron with a crust of rock on it, right? And most of the iron is molten, heated way beyond the melting point of iron, but then it's compressed so tightly by the self-gravitation of the Earth that you get extreme temperatures and pressures at the center of the Earth, and there's convection. The molten iron can move. You get electric currents set up. It's all governed by a very complicated branch of physics called magnetohydrodynamics. And they've tried to calculate, just based on the measurements of the Earth's magnetic field, which are done obviously outside the Earth. You can't go deep inside the Earth and measure the magnetic field, but you can make computer models of it. And this tends to be what the magnetic field lines look like deep inside the Earth in one of these computer models. Okay, they're all jumbled up like that. Looks sort of like hair or spaghetti or something. But the blue is supposed to represent south magnetic pole end, and the orange is the north magnetic pole end, and the field lines are going like that, and they get all jumbled up inside. You know, the Earth is heated from inside by nuclear decay of heavy elements left over from whatever the Earth formed from billions of years ago. In fact, if the Earth wasn't radioactive, we wouldn't be warm enough here to be for life to survive. Water would freeze, everything else. It's not just the sun that warms the Earth. The Earth is warming itself by these nuclear beta decays from deep inside it. And that was actually surmised. It was already figured out in the 1800s that the sun alone wasn't enough to keep the Earth as warm as it was. So they postulated there must be some source of energy from the Earth itself, but they didn't know what it was. It turned out to be a nuclear energy. So we're nuclear powered.